All right, one more time. Let me know if you can still see again. 1D kinematics. You could just you don't have to come off and mute. All right, bet. Cool. So what we have going on now is I wanted to kind of give you a preview of how I'm going to be doing things a little bit more forward. I want to use a software called Mentimeter to where we kind of introduced a little bit of kind of like a cool style, like quiz type of like some of the stuff that I've been doing. Now, this is not for a grade. This is just to kind of reinforce some of the vocab and things that concepts we talked about before. So let me go through the slides real quick. And then how we're going to go through this, we're going to go through the slides. I made some slides. If you were able to check out what I posted yesterday, where I said watch the video and the slides, and you were able to kind of see what we're going to go into. And I'm going to show you how you through the go through the practice problems. Let me see if I can add from right here without having to exit out. If not, I have to go back to the screen. Hold on real quick. And then after I go through the introduction of how I want you to kind of go through the practice problems and how you're supposed to go through them, I'll make sure. Yes, actually, I'm about to go to the next slide while I'm talking. I probably should have did that. So go to this website real quick and then join. If you're on your laptop, you can join your laptop, or you could just join your phone real quick. But yeah, after we do that, we'll go through the slides and I'll introduce you kind of some stuff with this group that I'm working with called the IBM Quantum Center, to really show you the reason why I'm kind of structuring the class like this. The reason why I structured the class, I don't want it to be very difficult. I want it to be very easy so you can understand the fundamentals, because there's actually an end goal that we all need to get to when it comes to understanding physics in general. So I hope this can bring a light of how class is going to be moving forward and what I want you guys to get out of this course for the semester. So let's get right into it. Um, Let me see if I can see. Let's see a couple of you joining right now. So I'll put the code in the chat if you can't already see it. If I can. It should be, yeah, 57844101.
I have a question. Is this recorded?
Yeah, I'm recording it.
Okay.
I'm getting some issues. I'm gonna have to leave and rejoin.
Okay, I'll see you when you come back. So that's the code for the site, menti.com. All right, let me go back to the presentation. To present, and then you should still see my screen. All right, cool, yeah. All right. Now the first thing, right? I did want you guys to kind of, as I open this link, look at this video. So the purpose of me showing you this video, right, was to pretty much take you through to where you can see pretty much how they kind of covered everything. Sorry, I was muted. I'll scroll over with the thumbnail. But the different parts of this video that they covered, they were able to go through and talk about kinematics. As you can see in the thumbnail, they have the same type of setup how I have, where they had the charts and the different types of vectors. Then started talking about individual quantities, different distance of displacement, speed and velocity, and then got into talking about constant speed and constant acceleration. So this video covers pretty much a whole entire thing of how we were able to do the same thing in class, right? So if you watch this for the first, let's say 20 minutes, you'll have a good overview, and then they go through an actual simple problem. So I advise you, when you have your own time, please go through this and watch this video and take your time with it, because I said a lot within the first 3 classes, but this video covers it all in 30 minutes, just in case you need to hear another voice. So that's why I wanted you guys to look at that before today. Now let's go back to Mentimeter, to where I want you all now, let's play around and see if we can see how we're doing. Like, once again, the code is in the chat, 57844109. Got about 11 people join. If you're still trying to get logged in, you can still join at any time, but let's go through some of these problems. So the questions are going to come up on your phone or whatever device you're using, and just pick the right answer or answer you feel is best. So what is a scalar? A quantity that's fully described by both magnitude and direction, a quantity that's fully described by magnitude alone. So a scalar is a quantity that's defined by magnitude alone. Magnitude, what we talked about before, is just a number, right? So 50 meters. So that's just 50 meters. That's how far I went, right? Next one. So what is a vector? Now, a vector is that a quantity that's fully described by magnitude and direction, or a quantity that's fully described by magnitude alone. Good, almost 100%. So a vector is a quantity that's fully described by both magnitude and direction. So instead of me just saying 50 meters west. So I added direction to it. So how far I went with the actual direction. So distance, right? What is distance? The definition of distance: the amount of ground that is covered, or the overall change of position from an object start to finish. Almost 100%. So good. So the amount of ground that is covered. So we talk about distance, we're just looking at the amount. So I went 50 meters. I just went 50 meters far. Didn't talk about which direction yet. So we could look at distance. We could kind of conclude as a scalar. So displacement, right? What is displacement? The amount of ground that is covered, or the overall change of position from the object from start to finish. Let's see what we got on that one. 100%. I give you guys a round of applause. Good job, good job, good job. I don't know if you hear me clapping, but 12 out of 12, overall change the position of the object from start to finish. So remember, going that house example, start to finish is where this really matters at. Start and finish, initial versus your final. So speed is a quantity that describes how fast or slow an object is moving, or is defined as the rate at which the object's position is changing. All right, we cooking in grease. All right, good job. 100%, good job. Describes how fast or slow an object is moving. Good. So velocity is a quantity that describes how fast or slow an object is moving, or is defined as the rate at which an object's position changes. 100% again, good job. Defined as the rate at which an object's position changes. So acceleration now. We look at acceleration. Is it the rate at which an object's velocity changes or the rate at which an object's speed changes? %. Again, good job, good job. Being very specific. When we're talking about acceleration, we're talking about the object's velocity. Why are we talking about the object's velocity? Because the rate of change of the object's velocity. So we're looking at the vector, not so much speed, which is the scalar. So now let's just go back and do kind of a review. Which quantities that we talked about so far are scalars? Displacement, distance, speed, velocity, or acceleration. And Mentimeter, you know, it doesn't let you pick more than one answer, so you can just pick one of the two. So there's two possible choices to be correct. Distance and speed are both the scalars. So now that we see distance and speed are scalars because they don't have any direction, you just talk about the magnitude alone. Let's see for the next question. Which quantities are the vectors? Between distance, displacement, speed, velocity, and acceleration. Which ones are the vectors? All right, almost 100%. So we got our three vectors, which would be displacement, velocity, and acceleration. Why are they vectors? Because they all require magnitude and a direction. So displacement, 50 meters west, velocity, 50 miles per hour, 50 meters per second north, and then acceleration, 50 meters per second squared west. So we got magnitude and we also have a direction. Now remember, these three quantities go together for us to describe motion. So we're going to see these later. All right, a little intermission real quick. I don't know if you guys are able to put in your names, but we've been keeping track of points. So we have our leaderboard. Let's see who's at the top. So we got Cassie, Cake. I don't know who's Cake. You probably didn't change your name. And then we got Ronald. All right. So still some time if you're trying to win the game for today. We got 5 more questions. All right. Now, these concepts were involved in here too. We got instantaneous speed of an object, right? So the instantaneous speed of an object is the speed that an object has at a given instant, or the rate at which an object covers distance. So the speed that an object has at any given instant. So this comes up when we start talking about an object's motion, and we might want to look at it at a certain time, right? Not just the overall or the average time. We want to look at a specific time. So just keep that in mind. So the average speed of an object is the rate at which an object covers distance, or the rate at which the object changes its position. Now, this is a little confusing, but let's think about it, right? The two concepts go together, right? The scalars go together and the vectors go together. So when we're talking about objects and speed, right, we're talking about the change of that scalar quantity before we're talking about change of position. So that would be distance, right? So the rate at which the object covers distance. The rate at which the object changes position would actually be its velocity. And why is it velocity for that second one? Is because we're talking about changing its position from its starting to its finish instead of how far it just went. Hopefully that's not as confusing as it came out. Now the average velocity of an object, going back to that same, difference, the rate at which the object covers its distance, or the rate at which an object changes its position. The rate at which an object changes its position. So we still need that initial and final. So every time we're talking about displacement, velocity, even acceleration, we need to know about that initial and that final. Initial and start and finish, start and finish. That's what makes the vector quantity. So then we have the average speed of an object, right? Now let's get into some equations, right? The average speed of an object is equal to distance over time or displacement over time. Remember, scalars go together, the vectors go together. Good, 100% correct. Good job. So we got the average speed of an object is equal to the distance over time. So it is position over time, but which quantity of position? The scalar distance. So average velocity of an object is equal to the distance over time or displacement over time. Scalars go together, vectors go together. %, correct again. Good job. Displacement over time. All right, last question, right? The acceleration of an object is equal to velocity over time or change of velocity over time. Close. Remember, I said this is the most important thing, the change of velocity over time. We're not just looking at velocity over time, it's the change, the rate. Acceleration is a rate of change, and we're looking at the rate of change in velocity over time. All right, let's see who came up on top today. So Cassie's our winner today. Then we got Carrie and we got Ronald. So give it up for Cassie. Congrats, congrats, congrats. All right, so now let's get into these slides. All right, so let's get into these slides. So hopefully that was a good, nice warm up for you guys to like get back in the frame of mind of what we talked about. We didn't see each other since last week, Wednesday, but really that's really how simple it is when it comes with physics. Just understanding those vocab and those baby definitional equations can really help build us a strong foundation, right? So if you haven't got a chance to look at the practice problems, they are due next week, but I want you to be able to, I want to stay on track with that timeline so we can keep it to move forward. But I want to show you how you can approach going through the problems as we have. I've given you the answers to the problems, but how you should go back and forth with them, right? So let's look. So this, remember, is our end goal, right? We want to be able to answer this Michael Jordan problem. Michael Jordan has said to have a hang time of 3 seconds, and we want to be able to use kinematic equations to determine the height in which MJ could leap if he was wearing, his Nike shoes and hang time of 3 seconds, right? So really the most important part is that first sentence. Michael Jordan said to have a hang time of 3 seconds. How do we figure out his hang time, which is how high he is above the ground, right? So when we're doing this, right, in these practice problems, that's our end goal. We have all these different topics, right? We have describing motion verbally, distance and displacement, all the way down to describing motion graphically. Then at the very end, we have free fall. So how do we go through all these topics to be able to get to free fall, which would be where the Michael Jordan problem is, to where we get one piece of information and then we solve it, right? So let's start going through some of these concepts, right? Oh, wait, I didn't mean to do that. Hold on. All right, right here. So starting off with just the beginner, right? We talked a lot about vectors versus scalars, right? But what is a scalar? A scalar is the quantity that is fully described by just its magnitude alone. So like I said before, 50 meters, just period, right? That's just the distance, how far you went, right? But if a vector, right, it has magnitude direction. So I have to say 50 meters plus a direction such as like east or west or north, south. So once I add a direction, now I have a vector, right? So now when we look at vectors versus scalars, we have different types of quantities, right? So we have distance and displacement. So distance is the amount of ground that's covered, right? While displacement is the overall change in the object's position from start to finish, right? So distance would be the scalar, while displacement would be the vector. Then the other two quantities that go together, right? We have speed and velocity. Speed is the quantity that describes how fast the solar object is moving, while velocity is the rate of change in the object's position, the rate at which an object's position changes. And that is, they're both representing position over time, but one is a vector and one is a scalar. Speed is a scalar, velocity is the vector. Then lastly, we have the quantity acceleration. Acceleration is rate at which the object's velocity changes. So the rate at which the velocity changes, or the rate at which the rate in object's position changes. So when you break them down, right, we have them that go into these buckets, like how we talked about earlier, right, and on the board. We have scalars, which are distance and speed, and then we have vectors, which are displacement, velocity, and acceleration. Now, really focusing on those three on the right, you'll see that we have that very much nice organization stack between them, right? So remember that for the moving forward. All right, so let's do a quick problem, right? So you have these slides too on Blackboard, and I want you to kind of play around with it. So now here's the problem, right? We want to describe verbally with distance and displacement, right? So let's see the difference between these two. For this problem, right, you run to your house for your friend that's 3 miles away, and then you walk home. So you go 3 miles to your friend's house and 3 miles back, right? So real quick, can someone answer the first part? You can either put in the chat or come off mute and say it out loud. What distance did you travel? In meters
You
or miles
you traveled 3 miles.
in total?
Wouldn't it be 3 plus 3?
I feel a debate going.
You run
Well, we
from
got
house different. The
Six
you
miles.
didn't walk.
miles.
It's 6. I didn't see that you didn't walk home.
Okay. Are we all consensus on 6 miles for the first one?
Wait. I'm gonna go with 3 miles.
Okay. So we got some 6. We got 3. I'm seeing 6 in the chat. If you put in the chat, I can see you putting 6 or whatever you put in the chat. All right. So you got some 6. We got some 3. All right. I'll keep that in mind. And then we got for the next one, right? So what was the displacement for the entire trip, right? So now we're talking about displacement.
Now it's 6 miles.
Okay. So we got 1 for 6 because you go 3 miles and you walk home.
It was
So
0.
Okay. So I got a 0. I still see 3 plus 3 equals 6. The second part we'll see about, okay, I see zeros. I see zeros, 0, displacement, zeros. All right, okay. So I got 6, I got 3, I got 0. Now, like I said, remember, distance, that's why I put review to the right, is the amount of ground covered, while displacement is the overall change in the position from start to finish. Distance is the scalar, displacement is the vector. So now as you go through the slides, I put it through. Here's the answer, right? So for the distance, right, it's 6 miles because you have 3 miles to your friend's house and 3 miles back home. So in total, you did go 6 miles, right? But now for the displacement, you actually have a displacement of 0 miles because you finished where you started. Very much that simple, right? I did go 3 miles, if you could tell by the walking. I went 3 miles to my east to go to my friend's house, but then I went 3 miles west back to my house. So essentially it's saying 3 minus 3, which is 0. Any questions about that? All right, I feel like we good, so I'll keep it moving. And now I have these slides are already up on Blackboard, so in your free time, this is how you can go through now. I put it in the same order, right? So let's now talk about the same type of problem. We're looking at the speed and velocity, right? So now, same trip, but now you're going 3 miles away in 30 minutes. You go to your friend's house, right? So it takes you 30 minutes to walk 3 miles, right? So now, then you immediately walk home, and it takes an hour on your return trip. So let's think about it, right? What was the average speed for the entire trip?
The average speed for the entire trip.
Mm-hmm.
3 miles in 30 minutes, and then 3 miles in 1 hour. So 1 mile every 10 minutes at the first trip, and then
Would it be the
1 mile
total
every 20.
miles?
Every
I
20.
see a 4.5 miles. What were
Total
you
miles
asking?
divided by total time?
Okay, so I like that. I like how you use overall miles over total time because it's still position over time, even if it was speed or velocity. So the total position.
3 over 30 is 10, and then 3 over 60 would be 2.
So if someone just came off from you to say, so think about it, the total miles
Total
over the total time.
the total time.
I think I seen it. Somebody put, what was it? Somebody put 4.5. Or would you get? Let me see if I got some 4 miles per hour.
In the first trip, you're going about 6 miles per hour. Correct?
You tell me.
Yes. If you go 3 miles in 30 minutes, you'll go 6 miles in an hour.
Okay. And then
6
The-
miles an hour in the first trip, and then the second trip they are going. Let's see. Well, 3 miles an hour. 6
Okay.
divided by 3 would be 2.
so you're saying 2.
Yeah.
All right, so we got a 2 and I got some 4s, right? Now for the second part, 2 and I got some 4s. I got a 4.5. All right, okay.
Oh, 6 plus 3 divided by 2, 4.5. I did it wrong.
I got a 4.5. So I got 6, I got 2, I got 4.5. No, I got 4, 2, 4.5. That's what I got.
I agree with the 4.5.
So I got 4.5 and some 4s. All right. Now for the velocity, what is the average velocity for the trip? I got a 0. I got some zeros. I got 1.5. Just a reminder too, speed is the quantity that describes how fast or slow an object is moving. Velocity is the rate of change that the object's position changes.
Velocity is displacement over time. You displace 0, so 0.
Okay. I think on that note, I'll show the answers. All right. So the average speed, right? So I heard somebody come up and said that you take the total total miles, like the total miles traveled over the total amount of time. So that's how you calculate it, right? So you actually have to do, you don't have to do the individual speeds and then divide it. What you would do is just take the total miles traveled, right? So we just found out the total distance traveled in the previous part was 6 miles, right? Now we just have a time with it. So we have 30 minutes and 1 hour. So the 30 minutes is half an hour. So you could say 1.5 hours in total, right? So then you just divide 6 by 1.5, and that's how we get the 4. But now when we talk about average velocity, we're talking about the displacement over time, which is the vector. And we already calculated in the previous one that the displacement was actually 0. So now if we were to take the displacement of 0 over the total time, we would just have 0 over time, whatever was 1.5, which is still 0. Does that make sense?
Yes, I got. Well, I understand how to calculate the average speed. Instead of doing it separately, I should have just combined the time, like, and make it 1.5 hours.
Cool. Now we got some math mistakes is all right, but as long as we understand the concepts, and like that's why I had to do the vocab, seeing that the vectors go together and the scalars go together. That was the goal of that. All right. Now let's move forward, right? Let's talk about some acceleration. So acceleration, right? This one, not so much math. This is very much just logical, right? A lot of us drive. Some of you drive. If you drive, give me a thumbs up or something in the chat that you drive so I can see who drives. All right, I'm seeing some people. Okay, so you drive, right? So acceleration, it could be easily modeled if we're talking about naming the controls on an automobile, right? Because that shows a very good example of acceleration, right? So acceleration is a vector described by the magnitude and direction, right? So when we talk about acceleration, let's remember about acceleration means the rate at which an object's velocity changes, right? So if you want to change the velocity of an object, you can change it just in thinking about it, right? By changing its magnitude. So the magnitude, how fast it is, like, so if you're going faster, going slower, or you could change its direction, right? So if I'm going left, right, forward, backwards, right? Now, with thinking about that, let's think logically, right? When we're changing the object's velocity, right? Can you name the 3 controls on an automobile that causes it to accelerate? So take what I just said and think about a car and the 3 controls on a car that could cause it to accelerate.
I don't drive, so I'll just say what drive, reverse, and it can't be neutral or park. I don't know the other controls other than those 4.
I'm saying control. Let me make it more specific. The three controls, as in like the three things that you use on the car to be able. Yeah, one of them, like three things you use on the car. So someone just put gas. So one, so like the gas. Someone said gas, brake, gear shift. I can't drive either. That's hilarious. All right. So you got gas, brake. I need three. I got gas and brake.
The
Gas,
clutch.
brake, steering wheel. Okay. So I got three. Gas, brake, steering wheel. Any more? Any others?
I don't know, the emergency brake.
So we got another brake, emergency brake. Okay. All right. I got what I was looking for though, but yes. So we have acceleration, which is the change of velocity, right? So the gas and the brake pedal, right? That changes the speed, obviously, the magnitude. So we're talking about forward, like how fast you go forward. Sorry, how fast you're going, or if you're going slowing down, right? But that one that really brings home about the vector part is that steering wheel, because you're changing from left to right, or going like if you're going reverse, the back way and the back corner too as well. So it really brings home about the concept of a vector is you have a magnitude and you have a direction. So if you change the direction, you'll be able to also change an object's acceleration as well. So that comes up very much big if we start talking about circular motion. So always remember this, right? So that was just to put it in context. All right, let's keep going, right? So now we have describing motion with diagrams, right? So this is another part. I got your review. Remember, we have our three concepts that we want to kind of put together: displacement, velocity, acceleration, right? So now, when we're looking at this diagram, right? This one too is not as much math. I want you to kind of put this together. Determine in these ones, right? If the car is accelerating or moving with a constant velocity. If the car is accelerating, determine the direction acceleration. Now provide your reasoning for each answer. Now I think this one, right? Let me see if I can. Give me 1 second. Uh, all right. Can you hear me?
Yes.
Okay. So I'm gonna put y'all in the breakout rooms for like 2 seconds, and then I'm gonna put, if you can. Did everyone see the problem?
No.
Hold on real quick. Let me just go back. So what I want you to do is determine the car's accelerating with constant velocity, right? So I think I'll put you in the 3 breakout rooms. So I want everyone to take a picture, if you can, just of it, just on your phone real quick, just so you have the problem. And I'm gonna do, actually, if I can, I'm gonna see how I can do it. Take a picture of it real quick. Like, give me thumbs up when you got a picture of it. This is also on Blackboard if you want to follow along with the slides, but just take a picture. Let me, if I start seeing some thumbs up, and I'll move on. All right, okay. So I've seen a lot of thumbs up. All right, let me go back over here. It was 5. Let me see if I could do 5. Hold on. All right.
Okay, sir, can I see the problem again? I'm sorry.
All right, yeah, hold on. You good? You got it?
Yeah, thanks.
All right. So now I'm gonna put y'all in the breakout rooms, and I'll pop in and I'll tell you which problem to do. So everyone's gonna just do one. And I want you to spend just a couple minutes just talking about it, and then come back with an answer and we'll discuss it. All right, ready? Go ahead. All right. So I'll go through. Hopefully that was good. Y'all got to talk about it and speak with each other. My first breakout room that did problem A. Could someone come off of mute and just talk to me what you guys were thinking, the answer that you came up with?
Based off of problem A, we had decided that the car is experiencing a constant velocity and not accelerating. And the reason why we feel that is because the images seem to appear at a similar rate in distance from each other.
Okay. I like that you gave me a reasoning with your decision. That's what I'm looking for, especially the reasoning. But I want you guys to hear each other speak before I reveal the answers. But I like how you presented the answer with the reasoning. All right. For my group B, problem B, can someone come off mute and tell me what you guys came up with?
I think the car is accelerating and moving to direction right because the space between each cars are increasing towards the right side.
Like I said, gave me an answer with justification for your reasoning. I'm liking it so far. I'm still gonna reveal the answers at the end, but everybody just take notes of what everybody's saying. Just listen, especially if you're going later, how you should be talking. Go ahead. For my problem C, can somebody come off of mute?
For problem C, we said that there is no acceleration because the stops in between the cars look about the same and there's no change in consistency, like the displacement is the same.
I like that word change. That word change was good. That really caught my attention. So like I said, I'm still gonna save the answers to the end, but I'm liking what I'm hearing so far. All right, next one. Problem D.
So sorry, we said it's accelerating because the first two cars are closer together, but the rest are further apart. So the rate of change is changing over time.
Ooh, I like that. I like that. The rate of change is changing over time. Okay. Somebody been paying attention. All right. Next one. Problem E.
We said that the car is accelerating to the left because there's more spaces between the cars on the left than on the right.
Gave me an answer, direction, and then also justification. Okay, I'm liking the way that you all presented your answers. Now, sometimes you might present it the right way, it might be wrong, but that's okay. But just at least glad that all you tried to give me something good. But I think for the most part, you guys are getting this one. So let's check out the answers, right? So for that first one, right, there is no acceleration. I think I heard this one correctly, right? There's no acceleration, and the reason behind that, the space in between the positions is constant, right? And then this indicates that it's a constant speed, so there's no acceleration, constant velocity as well. So now for this next one, right, there is acceleration in the direction we're going to is to the right. The position is definitely increasing, so that indicates that this is speeding up motion, so acceleration. And then because the object is speeding up, it has acceleration in the same direction that it's moving. So we have it speeding up to the right, so the acceleration is in the right. So now for this next one, I think I heard it correctly, was no. The positions in between them is constant. So the space in between is constant, so the speed is constant as well. The velocity is constant. So no acceleration. Then we go to the next one. We have the same setup pretty much as the first one, right? The spacing is increasing. So now we have a speed up. So it's yes and to the right. Then for the last one, right, we kind of seeing that you could say they're going to the left, accelerating to the left, or you could say that it's decreasing the pitches in between them to where it's slowing down. But either way, if you're looking from left to right, right to left, we still know that it's accelerating because we have it changed. And I think what somebody said it earlier, the rate it changed is changing over time. So you guys actually did go pretty good with that one. But like with these type of problems, when you're going through these by yourself, this is how it's supposed to look. You take your time, you come up with an answer, you figure out yourself, then look at the answers to see how close you were and go back and forth. Or you can even go backwards, look at the answers, and then kind of try and figure out how it goes. But this is how you want to take your time through it.
I had a question.
Can you hear me? Go ahead.
Yeah, so if you go back to the last slide,
Hold on. Yeah.
Okay, so you see on E. So whenever you said it doesn't matter if you read it from right to left, I've read it from right to left for E, and I felt like towards the end it was continuous. It didn't change, but it seemed like it's reversed, like it's backwards, like it was going slow at the end, and then it looks like it starts to pick up speed and accelerate forward in E, but it's the opposite.
What I meant to say is like this one, right, with E, right? Like if I look at it from where the E is all the way to the end, that would be left to right. So then if you look at it from left to right, you see that the spaces are getting closer, which means that it's changing, which would indicate it's slowing down. But because I don't know, did it tell you to look from right to left? It didn't tell you which way to look, right? So you could just assume like from left to right. But if you were to look at it, what I'm saying with this one, from right to left, where you looked at the very end, where you see the last car, where the yes is, but the car right before that, and then look at to where you get to the E, then it would appear that it was actually speeding up, but to the left, because the spaces are getting between bigger as you go to the left. But what I meant to say when I'm saying back and forth is, maybe you can look at it either way, is you see the spaces, the changing in the spaces, it's increased, like it's changing. So by just that change, either way, if you say it's increasing or decreasing, it's a change. And that change indicates acceleration. Now we just got to talk about which rate we were looking at to find a direction. Go ahead.
Okay. So for the most part for these, we read left to right, not right to left.
Have I been saying right to left?
Okay.
Because I might be saying right to left and meaning left to right. But it's just look at it from like how you normally would look at it. Like from this one right here, you will look at it from left to right. Yes.
Okay, that's what I figured. Okay.
So Medea,
Why
Say
did
it
you
again.
cut off?
me cut off this. Yes.
Okay.
What's happening? Okay, I'll just keep going. All right. Let me see with this one, right? I'll do the same type of problem with this one. Let's see how we get through this one. I'm gonna break you guys up again in the breakout rooms. So now this one, right? We have 3 different types of numerical graphs, right? Sorry, numerical tables, right? So we want to assume that the motion of each one is uniform between each one. What uniform means they're changing at the same rate. So you could say like you could kind of predict by the numbers. Let me just give you an example, right? In that first one that says snail, right? We can assume that the object is uniform, traveling is the motion is uniform, which means that at position 2 is going to move 11 feet again. So at position 2, what would that number be if it moves 11 feet again?
22.
Correct. So then at position 3, it moves what?
33.
Yes. So that's what that means by uniform. So at the rate which is changing is the same rate each time, right? Now, what we want to do is look at these numbers, right, and determine if there's acceleration. So now remember, what you have to do is pay attention to what's the quantity that we're looking at for each one, right? So look at the titles at the top. Like the first one says time and position, time and velocity, time and velocity. So look at them and then determine what acceleration is. So once again, same thing. Take a picture of it, thumbs up when y'all have a picture of it. I'm about to put y'all in breakout rooms again. Now, because I explained this one, I'm gonna make this one. I'm gonna give you. Actually, I'm really gonna time it. I'm gonna do like 2 minutes. All right, I'm seeing thumbs up. Let me go put y'all in the breakout rooms. And how does it go? Hold on real quick. It was Snail, Honda, and the Falcon. All right, so when you join your breakout room, you'll see which one that you're doing. Is this Cassie? Okay. Now that question, I'm used to Zoom, right? When I close out the rooms, is it just abrupt or is it a countdown?
There's a countdown.
Okay, wait. So the first time, how long was the countdown?
I guess 30 seconds.
And then did it close automatically, or like if I press it again, did it go all the way through, or did I close it like?
I didn't wait till the time. There's a button where you can click join the main room, and yeah, I clicked that.
Okay, I didn't know if I was just rushing y'all out of there because I didn't know if somebody would be talking and just be over. But
Yeah, I'm also new to it.
okay, all right. So let's go with. I don't know if you can see my screen, which you probably cannot. All right, you can see it now. Hold on. Okay, so with the screen, right? Where's my snail group?
There's no change in acceleration. It's consistently going 11 miles an hour or 11 feet a day per day. It goes 11, 12, 33, 44, 55, 50, 66. So no acceleration, no change.
Okay, so I like what you're trying to say, getting it there. Like you said, no acceleration, and started speaking about the change, right? Let's hold that. I'll make sure we go over the answers at the very end. Good job. Let me go Honda Group.
I wasn't finished calculating when the group ended, but what I was doing was I was trying to use the kinematic formula for acceleration, which is velocity over time, correct? Is that
I'll wait for you to tell me. I'm going for your explanation.
so I was going to plug in 54 over 0.5 over 0.5. 1 second, I need a calculator for that. I'm not sure what the acceleration is, but I see from the velocities that the acceleration is not changing. The velocity is constant. It's constantly going down, down in increments of 6.
So you say no acceleration.
No acceleration.
I think you just said the velocity is changing, so that's acceleration, isn't it?
Oh, we got a debate. Okay. Is that it? And you got a response or rebuttal? I love debates.
Nope, I'm looking through my notes frantically.
While you figure out the rebuttal, I'm gonna give you like 30 seconds. I'll let the Falcon Group go. Falcon Group.
We were saying that the acceleration is 36 meters per second squared down.
All right, you gave me a number. Can you give me a justification with your thought process?
Because between 0 and 1, it goes from 0 to 36. And it keeps going, or the velocity keeps changing at the same rate over the whole time.
So like we did the
Oh, sorry, go ahead.
between 0 and 1, like if you do the difference, it's 36 minus 36 minus 0 divided by 1, right? Final minus initial. I don't know.
No, that's exactly what I was looking for. I'm looking for you to say those words, final minus initial, because if you say final minus initial, you're speaking about change, right? And if we look at our review over to the top right corner, right, we have displacement, which is the overall change of position from start to finish. Velocity, the rate of change that an object's position changes, right? Then we have acceleration, which is the rate at which an object's velocity changes. This is important because even in that Honda Group, I started to hear it a little bit. You talked about the actual velocity, right? But remember when I did in the beginning, we're not talking about the velocity over time. We're talking about the change of velocity over time. And what does that lead us to? These answers right here, right? So when we look at it, right, we want to talk about each object and how it's moving and changing, right? So when we look at the first one, the first thing to pay attention to is the numbers. They're giving you the time and position. So we think about it, right? We need to find out if the velocity is changing over time. So we have the position, right? So the position, how the position related to the velocity. The velocity, as we see right above it, is the rate of change of an object an object's position changes, right? So the object's position changes. So how is the object's position changing, right? It's changing at a constant rate of 11, right? So if we were to plot this right, or just look at it right, the velocity would be constantly change. The velocity would be constantly 11 feet per day each time, right? So then that means that all these numbers will have 11, 11, 11, 11, 11, which means there's no change in the velocity. So that's why we have a zero acceleration for the first one. Now, if we move to the next one, right? We're now looking at the top, which is time versus velocity. So now we're actually looking at the numbers for the velocity, right? So because of that, we can actually look and see, is the velocity in this table changing? And what we can see is the velocity in this table is actually changing. So it's changing at a rate each time by about 12. So you see from 60 to 1, sorry, from 0 to 1, we change from 60 to 48. So that initial is 60, that final is 48, and we're going east. So we can see it's going down by 12. And it keeps going down by 12 every second, right? So now when we see the rate at which it's changing, the rate at which it's changing is 12 miles per hour per second, right? So that's what we have for acceleration, because it's the rate of change of the velocity. The rate the velocity is changing. The velocity is changing 12 miles per hour per second. All right, last one, we go to the Falcon, right? The Falcon 2, we want to see the time versus velocity. So we got what we're looking for. So now we just need to see if we see a change, right? Now, like they talked about before, they started at 0 and they went to 1. So the final minus initial, so the final is 36, and the initial was 0. So 36 minus 0, we have 36. And what are we looking at? Meters per second and then per second. So then we have the acceleration. It's meters per second per second. So 36 meters per second down, or 30 meters per second squared down. Any questions about that? I wanted to just make that's very clear. That was a mouthful. The explanation is underneath, but change in velocity, acceleration, the biggest thing to talk about right here when it comes to acceleration, change in velocity over time, change in velocity over time. Everyone in the chat, write change in velocity over time, change in velocity over time. I want to see it. Let me see it in the chat. Change in velocity over time. Change in velocity over time. There we go. That is acceleration. Change in velocity over time. If you ever get confused. All right. Let's go through this one right here. I think I'm going to do this one too as one more group one. So where we talk this one through, right? Now, you're not going to be able to probably draw if you got a piece of paper on, like that'd be fine. But what I want you to do is definitely when I'll hand you a printout with these to where you actually can draw through them. But take your time, and I want you to kind of, let's go through these and put them together, right? So we want to draw the lines of the curves that correlate to the word descriptions, right? So how would the position and time graph look if an object is either remaining at rest or moving, or if it's moving slow and then moving fast? Is it a straight line? Is it a curve? Is it a horizontal line? Like, what would it look like? So I'm gonna put you in breakout rooms real quick and just do it one more time. All right. The way the numbers are working is 1, 2, 3, 4, 5, 6. So go 1, 2, 3 are at the top, and then 4, 5, 6 at the bottom. So just join, and then we'll see probably be our last problem. We'll go through it. Then we'll just have to think before I close out for the night. All right. The rooms are open. Go ahead. You guys okay? Just join in the breakout rooms real quick. Is this Courtney? Okay.
I exited the meeting by accident. I'm not sure how to get back to my group.
No, that's fine. I'm bringing everybody back anyways.
Oh no, she was gonna show me the answer. Oh my gosh.
This
I just left in the middle of her talking by accident. Ugh.
is I'm about to show you the answer anyways.
Okay.
All right. You don't have to rush, but let's go through this just a little bit quickly so I can get you to the end and get you guys out of here on time. So remember, we have our displacement, velocity, acceleration. Those are our three quantities we're just talking about. So now when we look at this position in time graph, right? Let's consider that and tell me what you think this would look like if we draw it, right? So my first group, group number one.
For remaining at rest, it'll be a straight line.
How is that straight line looking?
Horizontal.
Okay. And for
And
moving,
slightly upwards or downward. Any is
Okay.
fine.
all right, cool. Like the explanation. For my group two, what do we have? For moving slow, moving fast.
For moving slow, me and Lakshmi said that the line would be very acute, almost horizontal, but very acute. The angle of the line would be very acute. And for an object moving fast, the angle of the line would be closer to 90 degrees and or obtuse, more obtuse. Or no, not even obtuse. It's just the closer to 90 degrees.
I like the geometry references. I see where you were going with that. And that's the first time in me teaching this that I've heard somebody use geometry references for the lines. So that was perfect. But I see where you're going. That was good. Give me my group three.
So we had said that if it's going in a positive direction, then it would be moving out from the vertex. And then if it was moving in a negative direction, it would be forming kind of an X going from the top left down to the bottom right.
Back again with the geometry references, vertex. I like that. And I see the vision of what you're trying to say coming from the, from the origin going through and then from the top, just going down, kind of like making an X. Okay. Group four.
I'm the one that missed the problem.
Well, I think I know who this was. We'll come back. We'll go right to group five. Go ahead, group five. Anybody from group five?
Yeah. What I got from it is they both have a positive velocity, initial velocity. So the slope is positive, and if it's speeding up, the slope is gonna become gonna be a concave up curve. And if it's slowing down, it's gonna be a concave down curve in the graph.
I like to use the vocab concave up, concave down. I like that. See what you're going with. I'm gonna show the answer at the end, but I like the direction that you're going. My group six, bring us home.
Yeah, so we said that line A would be going in like a curve from up to down, like how do I say this? Like an upside down parabola. On the right side, it'll be just going like from up to down, and then for B, it would be from up to down, but in like a curve down, if that makes sense. I don't know, but that's how I can explain it.
No, I like how it's difficult to explain because that's probably the hardest one to explain in words. But as long as you tried it, you see that. I like that you even established that it's going to be curves because you can see with the speeding up, speeding down. That's good. So let's look at it visually to kind of put it in context, right? But for general, like you guys did a good job of trying, and then also to like getting the concept of what these look like. So now we're just doing position and time right now. So we're going to do a lot more graphing next class to really kind of bring it all home. But let's just look at these answers to see how close you guys were, right? So for the first one, right? I think I heard it. I heard the first one, rest, would be a horizontal line. And then B, we're just looking at moving. We didn't specify how it was going to be, but it's just a slope line. So some light that's kind of up here. I know I heard for the second group, they talked about, you know, acute versus obtuse, I mean, and like some right angles, but that's the difference when we see going from the first one where we have that horizontal and just a slope line to now having two slope lines, right? Now, one is a little bit flatter than the other one to where it's almost looking horizontal. That would be the one moving slow. And then we have the next one, which is a little bit more higher, more slope, which is more into the right angle, like we're talking about the geometry, to where we could say it's moving fast. So that'd be the difference between moving fast and slow. Then I think I heard it correctly, right? When we talk about the next one, where we're moving in a positive, negative direction, we get this X, to where the first one is like, you know, coming out from the vertex or the origin, we're going up, right? And like to where we're going, it's like a acute angle. But if we're talking about changing in a negative direction, we're starting from the very top and we're going down. So decreasing the position, going down to a negative to make that X. Then let's go to the next one, 4, right? So when we have a constant moving speed, right, we have that straight slope line, right? But anytime we see some acceleration in the position time graph, right, we're going to see that curve. So it could be curved up, it could be curved down, but anytime we see acceleration, we're going to see it curved. That's a big thing to be able to remember, right? Now, when we start getting into 5 and 6, right, we start talking about what type of curve are we going to see, right? So in 5, the first one, right, we're moving in the positive direction and we're speeding up, right? So that's the one on the bottom, right? So you see like the word parabola be used to explain. So now we're going from the bottom all the way up, with the up concave up, I think somebody said. Then when we're doing the positive direction, but we're slowing down, it's like concave down. So like kind of like that upside down parabola where we're like going up, and then we see it to where like then it's starting to mellow you out at the top, right? So we're still moving in the positive direction, but we're slowing down. Now when we get to the last one, right, we talk about moving in the negative direction. Now if we're moving in the negative direction, we're speeding up, right? Now let's think about it, right? We're going down, but we're going down faster as time goes on. So we're going to have, you know, kind of like more horizontal curve, but as we start getting towards time moves on, it's going to be more steep in how we're going. So it's like almost like going downhill. Like if you're going down sledding, right? You're going downhill faster. If the slope is the hill is more steep. But then you got to think about it. The next one, right? When we have going in the negative direction but slowing down, right? We start off kind of high, right? But then we mellow out. Think about it like you're going down a slide, right? The slide is very high at the first, but then as the time goes on, it slows down to where you come at a nice like stop at the very end. So I think about it like a slide.
I'm confused. I can't lie. I was confused on 5. Like I was super like the straight lines I get, but once it starts to accelerate and curve, like in 5 and 6, 3, 4, 5, yeah, 5 and 6. Well, even the fourth one, it starts to confuse, like the line B. It just kind of confuses me because it's just hard for me to, for one, even understand the positive and negative. Like, is the negative, because I can't tell if 1, 2, 3, 4. The fifth one is positive or negative between the sixth one, because negative is going down, and maybe I'm reading them wrong, but if I look from top to bottom, it still looks like they both could be negative.
So I get what you're saying. So when we look at this one, when it says moving in the positive direction and moving in the negative direction, that's showing we have to start from the very top of what we're looking at. So we're looking at position and time. So what we're looking at is the change in position. So is my change in position for it to move in the positive direction, but it's speeding up. So we're still moving in the positive direction, we're changing positively. So our position is increasing as time is going on, right? Like going up. So that would be moving in the positive direction versus moving in the negative direction is my position is decreasing as time is going on. So that's where we're starting up higher and then we're going down as time. So that's what the curves with the positive and negative, you could see like that, right? But the curve part really shows acceleration, because someone said it earlier in class, the rate at which my position is changing is changing. What that means is the rate that my position is changing is not constant. That straight line shows that my rate that my position is changing is constant. So if we were to take that slope of that, it would be a horizontal line, which means it's the same rate of change each time. But for like 4 with that curve, What it's saying is the rate of change in my position, that rate of change that my position is changing, which means that each time if I was to take the slope of that line, I would get a different rate each time, which means that if I was to take the slope of that line, then that line would be a slope line instead of it being a horizontal line, which then in turn, the slope of that line would be a horizontal line, which means constant acceleration. This is going to be very confusing for me just talking about it, but in next class, we're going to go see way more examples of this. So I'm glad that we stopped right here for today. And then on Monday, hopefully we could do this. Either way, if we don't have it in person or if we have it virtual, we'll still be able to do it this way so we could finish this up and I could really bring this home. I know that was a lot, but did that make you feel at least a little bit more comfortable?
With the first part, honestly, I'm not comfortable with the new part that we learned today, with the motion in the snail. Like once we got to that point, I just got I didn't really understand it well.
You have to I kind of get these exercises. These exercises are more so trying to get you to visualize what motion looks like on a paper. Like everything we've done has just, whether through a picture or through numbers, describing motion.
Right. It's
You
just
have to-
easier when he's showing us pictures, like visuals in the classroom versus this, and we can actually see like real examples in real time.
I get what you're saying. Yeah, these is just to get us started, but you'll get more concrete ones as we go through. But these are just to get you started with how the visuals, the graph is. But I'm trying to, these are really not to be as math heavy too. So it's just kind of like a lot more conceptual. But let me stop right there because I want to cover this real quick because I want to introduce you to this before I let you guys out of here. I know we're a little bit over time. Hold on. So I remember we were at position and time graphs. All right. So let me click out. Now, this thing right here, right? So this is the IBM HBCU Quantum Center, right? So as you know, UDC is a HBCU, right? So with UDC being, why do you keep playing? I'm sorry. Well, UDC being an HBCU, right? Well, UDC being an HBCU, you guys are qualified to be part of IBM HBCU Quantum Center. So I don't know if you heard anything in the news about quantum computing, right? Quantum computing, quantum sensors, quantum networking, like communications, all this stuff is a new future technology that's coming out, and it's based off of quantum physics, right? So a lot of the stuff that we see in nature, we try and replicate with technology. You see the same thing with AI, right? We're doing machine learning. Machine learning is just replicating how our brains learn, and we're using computers to help see if they can honestly do tasks on their own. Now, the difference is right now, AI is not new. AI was talked about 30, 40, 50 years ago, to be honest with you. All this stuff is old, even especially in the last 20 years. You see in the early 2000s, AI was talked about machine learning, all this stuff, right? We're just now starting to see, I know, you just hit your head. Okay. I know, we're just now starting to see the effects of AI right now at a large scale. So,
Hey,
what I'm
Nick.
about to say that is, yes.
Nick?
All right, so now, with that being said within the last coming forward, right? We're going to see the effects of quantum computing later on, right? But the actual learning how it works and understanding it is now. And I say that to say is you guys have a perfect opportunity with you being at an HBCU to be a part of a great center that not only funds students for opportunities, funds students to go to conferences, funds students to learn about research and anything comes to about that.
Nicholas.
All right.
Do they offer tutoring?
Tutoring? When it comes in respect to, let me find out. So this is a quick video. Can you hear my audio? Were you able to hear that? Or do I have to share my audio?
No, I did not hear that.
Okay. Don't even worry about it. All right. I don't know how to share audio, but what I'm going to do is I'm going to actually drop the, in the chat. It's like 2 minutes. So you can just watch on your own. Hold on. But this will tell you pretty much more about the center. And give you an idea what I'm talking about. And if you're interested, please look at it, right? Now, Why did I bring that up? Hold on. Almost done. We're almost done, buddy. I know. Because through the IBM HPC Quantum Center, I'm working on it to where I did some of these questions earlier last semester where I just took some of the content from the site. But this semester, we should be able to get access to the site to where we can start doing modules and different types of quantum computing things where you can actually learn some stuff about quantum computing while we're taking Physics 1, right? So there's this site, if you can see, it's called Black Opal, right? Black Opal, they are a group who actually has their own quantum computing quantum company, right? They do, I think, I don't know what type of quantum computing, what type of they're doing, but they actually have their own company. But what they're doing at the company, they also do quantum computing education as well. So they come up with these modules and they tell you all the things to help you learn quantum computing at a very easy scale, right? And it's very simple. It's very much little math and more so just understanding concepts, just kind of how I like to teach the physics. Now, I'll drop this link in the chat as well too. So if you want to sign up for free and play around with it to get some experience with it, then you can go ahead. But this we'll be working with throughout the semester to give you an idea of what's going to move forward so you get the basics of quantum computing. And I'll just put the link in the chat and I'm sharing my screen.
So wait, I'm confused. So the actual club, is that the link that's at the bottom that I just clicked on?
Oh, so the IBM Quantum Center is the center, right? I don't know if you're referring to, there also is a UDC Quantum Literacy Club on campus. You guys should, if you're interested in this quantum stuff, you should join that club too. I'll also be putting information about that as I see. But the IBM Quantum Center, if you watch that video and you like it, just make sure you send me an email or you just mention to me, hey, professor, I'm interested in learning about more about it so I can get you connected with them as quickly as possible, And if you are interested, one of the first things you can do is get this certification. That's the biggest thing too. This Black Opal group, what I just put in there, they give out a certification for quantum computing, which you could put on your resume. You could actually use for LinkedIn. And the IBM Quantum Center is sponsoring students to be able to get it. And it's free. It's free content. So if you want to go ahead and get the certification, that look good on your resume, and you can be able to market yourself and learn a new skill, just let me know ASAP.
Thank you.
No problem. And with that, all I need is some feedback before we get out of here. If you still got your phones open, I don't know if you might do, but if you still got this open, give me some feedback on how today was, and then I'll let you guys get out of here.
I like it, but whenever we do virtual,
Wait, no, don't tell me. Like, put it in the thing.
Huh?
Type it in the thing so it pops up on the screen.
Oh.
If you still have the app open, if you type on the screen, you're able to it'll pop up. The code is still the same if you do close it out already. 57844109. Okay, all right. And don't give me fluff. Be honest. All right. Okay. Cool. Now I will let Verbal come off if you guys want to come off from you to say anything.
No, I was going to say, I like that. It's really nice. I like the way you explain it. It feels like it's class. It's just when we're being introduced to new stuff, I like how in class you always draw everything out so it's easier for us to see it.
Like on a board?
Mm-hmm.
All right, I got you. So we're probably going to do, if we're in person, we're going to do probably the same thing, like with this on the computer, but I'll still have the board. So I'll go back and forth between the board and the computer.
Oh, thank you.
No problem. It's just that I can only do this virtual, but I usually, the way the classroom is set up, I know I have the board, but I also try to do the computer at the same time. So we make sure you use much and it'll work well. So Monday should be the first time us playing with it together. So we'll go through it and see how it goes. But in the meantime, right, please look at the practice problems, start looking at them, watch the YouTube video. if you please go look at the slides. All these slides are already on Blackboard, so get ahead of me, look at it so you can be prepared for Monday. Because if we can get through Monday first, I want to run through the practice exam. This is not a graded exam, but I want us to try the practice exam as soon as possible so you can see where you guys are with these problems. So if you get ahead over this weekend, we can move faster to where we can get done with this and then move on to the next unit. Understood? I'm seeing thumbs up.
Thank you.
No problem. I'll see you guys on Monday.
See you Monday. Have a safe
Thank
weekend.
you.
Yes, everybody stay safe, stay warm, stay off the roads.
Professor, I have a question.
Hold on, let me stop the recording.